I'm happy you're asking questions. Let me just address the questions you've already asked and then we will continue. Okay. So, one was a technical question that was about the antisymmetric part and how do we apply the magnetic moment operator. So, I have sum over I, Qi, sigma 3I, okay, which means that this is the Q1 operator sigma 3 1 plus Q2 sigma 3 2 plus Q3 sigma 3 3, okay, acting on the state, right? I mean, they will also be the other side. So, the safest bet is to not do any shortcuts and apply each one. So, this will act on the first particle. Let us say it is, let's take an example of UUD up down. I mean, I'm just giving an example. So, then you can see that this will act on, this will give you 2/3 acting on the U state, this will give you 2/3 acting on this U state, this will give you minus 1/3 acting on this state, and of course, sigma 3 will be plus, and here it will be plus, and here it will be minus, right? So, you will be able to do the direct product and multiply the result and get the answer, right? That is the simplest way. Now, when we had completely symmetric state, so let's call it P symmetric or symmetric P, I don't remember what I called it. Either the neutron or proton is completely symmetric. Then of course, since it is symmetric, as somebody pointed out, under pairwise exchange, right? So therefore, I can take any one of these operators, either 1 or 2 or 3, and act that thing and then multiply by 3 times, right? If it is completely antisymmetric state, then of course it gives you a minus sign, right? Each exchange gives you a minus sign. So you can see that two of them will, when you flip them, you will get one relative sign which will cancel and then one of them will be left over. Or as I said, if you are not sure how to do this, just do each one. It just takes 10 minutes to complete this exercise. Is that clear? Now that we have shown, so let me finish off another question also, a very nice question. Can we calculate the absolute values?
But in this argument, there is a problem. If that is total antisymmetric, then we can instead also one and second particle. So
yeah, everything it is antisymmetric. See, you can write some piece and then do a pairwise exchange of say 1 2 and 2 3 and write the other terms, right? And they will have a relative sign, right? That means that if I am exchanging the 1 and 2, then you can see that, and that gives me a relative minus sign. Then whatever is acting on the first state, because now, okay, let us call this U up. Now, and let us call this D down, just to be very clear, okay? And then this is some X, and this has some Y. Now, I am interchanging 1 and 2, so this will have D down and U up, right? But it will have a minus sign. So that means you can see that the Q1 operator acting here and the Q2 operator acting here will come with a minus sign, right? Is it clear?
But I think we have to change in and out both states. Means if
yeah. I mean, no, I mean you have that you have to do because it's a matrix element, right? So you have to do it on both sides. But I'm just telling you that if you want to count like this, then you see the operator acts only on one side, right? So this is some operator acting on some state. So this is the operator. So this is the whole state. So okay, so the second term when it acts, and this operator is a sum over operators acting on 1, 2 and 3, right? So when I interchange 1 and 2, the part acting on 1 and the part acting on 2 would be the same with a minus sign. Is it clear? Or if you want, do O1, apply the thing, O2 apply, O3 apply, and then when you see the answer, you will understand where the antisymmetry lies, because you will see the cancellation, then you will understand. Is it clear? Now the other question was, see, we found the magnetic moment of the neutron, we found the magnetic moment of the proton, and then we took the ratio. So the thing is, we have actually found the absolute magnetic moments of the neutron and proton within this model, but you will find that this value that you get is not so good, it doesn't have very good agreement with the experimental numbers, but usually ratios are much better understood. So ratios are more stable, which is why always, although we calculated absolutely the values of mu1 and mu p, we are actually asking for comparison with the ratio, because many errors that happen in the matrix element, when you take a ratio, there is some overall error normalization gets cancelled out, and therefore the ratio is much more stable, and that is why we compared only the ratio. That was the second question. Now the third question is, now I have a symmetric state in spin and flavor. So this is symmetric. Yeah, 1 second, let me just write this, then I'll listen to you. Spin and flavor, completely symmetric, right? And PA, I'll write this and then ask what the question was. Completely anti-symmetric in spin and flavor. Okay, what was your question? Somebody said something?
Ma'am, I was asking like, yes ma'am, Krishna.
Yeah.
Ma'am, I was asking,
Yeah.
here like calculate using the quark constant, we calculate the magnetic moment.
Yeah.
So can you find absolute values for mu n and up using that calculation?
That's what you have done, no? That's what you did. You found out mu n and mu p and only then took the ratio, right?
Yes ma'am. Ma'am, I calculated in terms of up quark and down quark magnetic moment, and then I took the ratio. I did not find absolute values.
No, what you found out was the...
I kept.
No, I mean, okay, there is a mu bar over there. There is a mu bar there which was E by 2mi, and you have to put in some value there. Yes, I agree. I mean, but up to that value, yes, there is some prediction. That again is a model, right? There are many models which can give absolute predictions. For example, there are quark models, very popular bag model, which actually try to do exact calculations. But of course, I mean, they get some things right and some things are approximations. Okay. And the main reason they fail, and we will see that later, is because QCD is a theory of strong interactions. We will see much later, and because of that, perturbation theory doesn't work, and therefore many of these results which you are doing at low energies, the coupling constant is large. I don't know whether this will make sense to you right now. We will answer this question some 25 lectures down the line. Okay, but there are models, there are quark models which are approximations and work in certain frameworks. Okay, you can actually predict the absolute values of these quantities. But here, of course, as I said, even if you can predict the absolute values of quantities, very often you take ratios because ratio is more stable. Okay. Now let me come to this question. So what we have found is that this agrees with the magnetic moment calculation and this doesn't agree with the magnetic moment calculation, right? That's what you people have done as homework. Now we know that the proton is a fermion, right? It cannot have a completely symmetric matrix element. Therefore, it must have some component called color in which it is completely antisymmetric, and therefore the net wave function. So all these are direct product, right? All these are direct products. So okay, since this part of the wave function gives you magnetic moment results or predictions which are in agreement with the data, therefore to make yourself a completely antisymmetric fermionic wave function, there must be some extra piece, and that we postulate is the color quantum number, and the color part of the wave function is antisymmetric. Is it clear? And this is completely identical, so I will remove this since this is not the right answer. This is completely in analogy with the delta part of the wave function, which was also completely symmetric in spin and flavor, and therefore also needed a color antisymmetric part. Is it clear? And I wrote down for you an omega also, right? And this has the same prediction because this was the S. Again the same thing. Exactly like this was either UUU or DDD or DDD. The two of them were this, and this is the other third one. So all these baryons which you observe in nature, in fact this was predicted from the nature of the model. This is the 10th member of the decuplet, and therefore from the spectroscopy or the observed baryons that you find in nature, you predict that there must be a color antisymmetric part of the wave function, and this is your indirect evidence for color. Okay, and when we come to scattering cross sections, as I said, we will talk about direct evidence for color. Right now we have just said that we motivate that there is a color quantum number, and we also postulate that this color is confined, and therefore quarks are not seen as individual quarks but are seen in terms of the mesons and baryons, which are the hadrons that you see in nature. So now there was a mistake in the last. Have I answered all the questions? Something got left out. The baryon decouplet. Yeah, before I go to that, I want to stay with the mesons. So there was a mistake. So let me just write it down. I am sorry for this. Sorry means not desperately sorry. There will be mistakes all the time. Please find them out and correct them. So I thank Jatin for pointing this out to me. This was when we wrote the pi plus pi minus pi 0. I will annotate the video so that I mark where it is the mistake, because I can't correct it otherwise. So we had said u d bar and u bar d, and this should have been the 0 charge one, which should have been u bar minus d d bar by root 2, and I had written this. First of all, these two have opposite charges, so you can't even combine them in a linear combination. So that was obviously wrong, and what I wanted to do was write this. Okay, I am sorry about that. So please correct it in your notes if you are taking notes, or next time you see that class video, you please realize that that is wrong. As I said, I'll try to annotate that video. So that is one point. The other point was, I realized when talking to Jatin yesterday, he was clearing some doubts since he couldn't attend the lecture, is the difference between the SU2 that we talked about in terms of up and down spins, where we had up, 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 down. Sorry, let's write them in order. Down, down, up, down, plus down, up by root 2. And this was the S is equal to 1, and S is equal to 0 was up, down, minus down, up by root 2. I hope you remember this. We had written 2 cross 2 is equal to 3 plus 1. So this is the symmetric. S is equal to 1, Sz is 1, minus 1 and 0, and this is the S is equal to 0, completely antisymmetric. This is the completely symmetric one. Okay. So I had said that because of charge conjugation, we have a minus sign because the charge conjugate of D is not D bar but minus D bar. Okay, and therefore this minus sign came. You can think of it as UU bar plus D minus D bar by root 2. Okay. However, you must remember that this is not SU2. This is SU3 flavor. Okay. The reason that this is SU3 flavor is that, you remember, it's a technical point but very important. SU2 has only one fundamental representation. SU3 has two fundamental representations, which are these two. This was called 3, this was called 3 bar. Okay. And when we want to talk about mesons, unlike baryons, we have mesons are made up of quark anti-quark pairs, right? And therefore I must have an anti-quark, which means I cannot talk about SU2 at all. Even though I keep talking about pi's being the SU2 subgroup of the SU3, that is true, but on the other hand, these U's and D's are actually part of SU3 flavor because there is no D bar unless you have SU3 algebra. Okay. This is why, in fact, the charge conjugate to the state was not the state, which is up, down, or up UU bar plus DD bar by root 2, but the charge conjugate of this, if you remember, was the eta, which was this. Why is that so? Because we had 3 cross 3 bar was 8 plus 1. This is your meson octet. This was the singlet. What was the singlet? The singlet was just the trace, right? UU bar plus DD bar plus SS bar by root 3. So I have identified one neutral state, the second neutral state, and the third one I identify as being orthogonal to the other two. And therefore, this must be there because it is a true SU3 object and not an SU2 object. So I was, I think I didn't kind of emphasize that enough in the previous lecture. So the one, there's a mistake in the definition of pi naught, and 2, I am elaborating more on why the charge conjugate of this was not this, but it was this. Is it clear? Is it clear? That's because you have full SU3 in order to accommodate the antiquarks. If you have SU2, you can talk about UD. So you can talk about baryons. So you can talk about the delta baryons, which we talked about. Okay. So 2 cross 2 cross 2 was 4 plus 2 plus 2, and the delta baryons belonged in that 4. That's why there are 4 delta baryons. So I am done with spectroscopy. Are there any other questions? The baryon decuplet. What are the states? Right?
Yes, baryon octet.
Oh, baryon octet. Okay, baryon octet. What are the states? So for that you have to go back to writing. What did you try to do? I mean, did you try to do using the Clebsch-Gordons, or did you try to do it using the vectors symbols?
What now?
No, how did you try to do? See, there's a baryon octet, right? So the baryon octet.
So we in this hexagon, we horizontal axis is isospin.
Yeah.
Vertical axis is strangeness.
Why actually? Why?
There is one diagonal axis also of charge.
That's okay. Yeah, that will get fixed, right? Yeah, correct. Yeah. Yeah. So what did you do here? So for example, here you will have your sigmas, right? So what is it that you're doing? You're having here. So this is your baryon. So 3 cross 3 cross 3, right? So this is 6 plus 3 bar cross 3, and then you get your whatever 10 plus 8 plus 8 plus 1. Okay. So how and these combinations of these 8s were what you got as proton and neutron, right? Now how do you actually construct these states? That is the question, right? Yeah.
Are the both eights same?
Are the?
Both eights are same.
This is mixed symmetric. This is C. Okay, maybe it went too fast. So we have two parts, right? So this 8, maybe I will write here mixed symmetric, and this 8 came from the mixed antisymmetric, right? Okay. 6 cross 3 gave a 10 plus 8, and a 3 bar cross 3 gave you an 8 plus 1. So what happens here, this 10 is completely symmetric under the interchange of all 3, whereas 8 ms this is symmetric. See, this is symmetric under 1 2, right? This is antisymmetric under 1 2, and this is of course no particular symmetry. So you take a symmetric under 1 2 and cross it with 3. So this is symmetric under 1 2 but has no symmetry under the third interchange, right? Now this is antisymmetric in 1 2. So when you do 3 bar cross 3, this will be antisymmetric under the 1 2 exchange, and the third particle has no particular symmetry, and this is the completely antisymmetric object. Is it clear?
The octet you have drawn here.
Yes.
Neutron,
Yeah.
to which 8 does it belong?
That is what I'm saying. No, that is the whole point, that this is not neither this nor this is the 8. We just showed that P and N are a combination of these two, right?
Yes.
So now I have here, so this is the flavor, right? But now in spin I have 2 cross 2 cross, the spin is still in SU2, right? And my wave function is a direct product of this state and this state. And what was 2 cross 2 was 3 plus 1. See, there is no bar over here. There is no bar because there is only one fundamental representation, right? Cross 2. Now again, this is the completely symmetric object, right? So when this 3 goes with this 2, I get a completely symmetric 4 plus a 2 which is mixed symmetric, right? And then you get a 2 which is coming from the antisymmetry in 1 2 and this 2. So it is a mixed antisymmetric. So this is my combination over here. So this is what I called phi ms phi Ma. This was my chi Ms, chi Ma. And my protons or neutrons was 1 by root 2 phi Ms, chi Ms plus, I mean, I am not writing the other one because now we have shown that this is the one, right? Of course, times the direct product in the color. Is it clear?
Yes.
Yeah. So to construct these states is not straightforward. All I want to point out is that here you should look at the Y quantum number and the isospin quantum numbers. So what do you have here? Yeah. Yeah, there was a question?
No.
Okay, so here what you're doing is you're taking I, whatever I cross I, right? So then you will have so many combinations. So this is the isospin, one combination, right? This is the isospin, half combination. So the way you look at it is this. This is only UD. So let me write it in terms of UD alone, okay? This is UD alone, okay? So let me give an example because there are 3 quarks, so let me call it UUD alone, okay? So UUU, let me put it over here, UUU was I is equal to 3 half and that comes in the delta part, right? So I have to start with the 8 which is UUD or this is UDU. Is it clear? So this is I3 is half, half minus half. So this is I3 is half, sorry what have I written here? And this is I3 is minus half plus half is minus half, right? This is plus half. Is it clear? The other way you can combine this is by having one strange quark here. This is UUS. So what have I done? I have replaced the D by an S. So what do I have here? I can have UUS. This will be UDS and this will be DDS. So you can see as I go from right to left, I am replacing one D with one U, one U with one D, and here this line has one S always. The actual state, the construction of the state is complicated. You will have to do the Clebsch-Gordon coefficients, right? But the quark content of these states is very clear. That's why this will be half plus half is 1. So I is equal to 1. So I3 is equal to 1. This is half minus half is 0 and S has no isospin. So this is 0. This is minus half 0. So this is minus 1. Is it clear? Now look at the charges. This is 2/3 minus 1/3. This is 0 and this is minus. Similarly, you can see this is plus and this is 0. And you can construct like that. So this will be cascade, 0 and minus. So what will this be? I will start with 2 S's. Is it clear? So I have no S's, 1 S, 2 S. Okay? And then this will be 0 and this will be minus. So those are the, and you can write down the Y's appropriately. For every strangeness, you will get an extra minus 1 in Y. Is it okay? So this is how you construct this octet. So the quark content I can tell you. So for example, if you look at this state, it will contain UUD in various combinations, right? We wrote that whole wave function down last class. But basically for proton, there are 2 U's and a D. That's what I am writing here. For the neutron, there will be 2 D's and a U. Similarly, this will be UUS, UDS, DDS and so on. Okay? So this is I is equal to 1, I3 is equal to 1, I is equal to 1, I3 equal to 0, I is equal to 1, I3 is equal to minus 1. However, and this is I is equal to half, I is equal to half, okay, this combination, there is one more left out, which is I is equal to 0, I3 is equal to 0, and that is also here, it's called lambda. So lambda and sigma have both UDS, but you have to construct the state so that they are orthogonal to each other. No, we are not going to do those state constructions. The reason we are doing this whole exercise is to understand that there is an underlying symmetry, which is an approximate symmetry, one moment, and to use this to make a calculation of, say, the magnetic moment or even the structure of the delta states, and therefore to postulate that there must be some antisymmetric part of the wave function which we assign as color. Okay, ask the question now. Somebody had a question.
No, ma'am.
Okay, fine. Is it clear now? So I am not going to actually sit down and write down all these complicated states, but however you understand how the quark content of these states comes, right? Right? So as long as you have 3 quarks which are part of U and D, okay, they can have, see, this is the isospin. Okay, fine. So what we have is that this is an approximate SU3 flavor, right? So U, I told you, has I3 plus half, and D has I3 minus half, and S has later on when we do weak interactions and we discover the charm, then of course the S strangeness and the charm will also go into an isospin doublet. But in this quark model analysis, this is what we have, and therefore every time you add an S, you can see that 2 S's means there is only I is equal to half. So this is an I equal to half state because there are 2 S's. This is an I equal to half state because of this 2 U's and a D. But you can do the counting, you can actually write them all down by looking at the Clebsch-Gordon coefficient of 3 cross 3 cross 3 and then writing them all down as in there according to the symmetry principles, right? Is it okay? Can I take this off?
Ma'am,
Yes.
I have a question. How we will decide value of i's? Means you are in middle horizontal line you are saying I equal to 1 and upper horizontal line you are saying I equal to half. How we will decide it?
Yes, but because that is how it comes, no? See, you're doing here, when you're doing this 3 cross 3 cross 3, right? You see what you're doing. You're taking 3 cross 3 cross 3 with one of them having isospin 0, right? So what is possible then? I can take this off, right? I can take this off. I'll take this off. I can take this off here. So you think of this. I have 3 cross 3 which can be either U or D, and let's say the last one is the strange quark. So it has isospin 0. So it's the same argument, right? Each one has isospin half. So I can have two possibilities. If I cross 2 I equal to half, I get I equal to 1, or I can get I equal to 0, right? That's exactly what I have here. So if I have I equal to 1, there must be 3 states which are sigma plus, sigma 0 and sigma minus. And if I have I equal to 0, I must have one state which is the lambda 0. Okay. So this is how you are going to sit and write down all of them. Whereas what happens here, I am doing 3 cross 3 cross 3 with 2 of them having I is equal to 0, right? So then I can have only I equal to half state. So here, now let's write, this is, let's call it A. The second one, I am having 3 cross 3 cross 3, where this has isospin 0, this has isospin 0. So the only thing you have is isospin half, which can be plus half or minus half, right? That's all. So those are those 2 states. So what we are doing is we are counting on the y-axis. I am adding 0 strangeness, 1 strangeness, 2 strangeness. So that will allow only that much isospin. So isospin over here is only due to the U and D quarks. And going right to left is the projections of the I3 operator. You can see that because when I is equal to 1, I3 is 1, 0, minus 1. When I is equal to half, I3 is half minus half. Here again half minus half. And when I is equal to 0, I3 is equal to 0. That's all. There are no more states. So we have counted them one by one in order. Is it clear?
Okay.
Good.
Okay. Yes.
Okay, very good. I hope no one is speaking, means they have understood.
Reference where we can find some examples where how to write quark states. For example, the UDS has 6 states. So how do we write the 6 quark states?
It is there in Halzen. Halzen has enumerated the states.
Mostly the examples of problems.
Oh, I see. Uh, let us see.
Trying to solve some problems in Hausen's book, which asks us to write the quark content or the quark states on
Yeah.
the flavor part.
Yeah.
But I could not write them. For example,
Oh.
DDS or UDS. So UDS will have 6 states and DDS will have 3 states. So Hausen had an exercise on writing the states.
Yes, that is true.
So if I could look at some examples where
I mean, the SU2, SU3 group theory is explained very nicely in Halzen, sorry, in Lichtenberg. But whether the quark states, I think the quark states are there in many books. But let me just see. I have Halzen in front of me. Let me see what exactly he has asked and what it is that you could not do.
And what I am talking about is problem number 2.11 and 2.12 in chapter 2.
2.11 and 2.12.
Page number 52.
Yeah, I found it, yeah. Okay, yeah, so he just wants you to enumerate the states. So what was the difficulty with writing this? For example, if you look at page 357, he has given the listing for 2.12, the answers. He has given answers to some random number of questions, right? So 2.12, you can actually see the structure. But the way to do it is to actually write down all the states and then to combine them according to, oh God, I just removed everything, to combine them according to the symmetries that we have got. See, they all have to fit into those symmetries, right? So they will not give you, okay, maybe I will do this in some tutorial session, okay? I will work out these things in some tutorial session if you are not comfortable with doing this. So either you can directly write it from the Clebsch-Gordon coefficients, or we can do this, whatever, you keep writing the symmetries down and then extracting them, writing orthogonal states, and we will find them out, okay? I will do it in some tutorial session. I don't want to do it now because I wanted to start something, and if I don't start it now, then I will not get anywhere with it. So, fine. I'm not sure. Prabhat, have you done this? I'm not sure. If you're not comfortable with it, I will do it in some tutorial session. Okay. Maybe I will work it out and send it around or something. Huh? Yeah, I think probably I will work it out and send it around.
Hello?
Yeah. Yeah.
Yes.
Yeah. So, but then one remark I wanted to make, which I forgot. So we wrote, for example, ud bar, and we called it the pi plus. Okay, and this is part of what we call the meson octet. But I want to remind you about one thing. This is part of what is called the pseudoscalar meson octet. Okay, that is because the spins of these two always combine to 0. So these are all spin 0 objects. But equally well, these spins could have combined to form a spin 1 object. When it's spin 1, it's called a vector meson. And there's an octet exactly identical to the pi object, okay, and they're just more massive than these objects, and they are called the vector meson octet. So this is called the pi meson. This will be called the identical object. This is also ud bar, but with spin 1 will be called the rho meson. Just like we had pi plus minus 0, there will be rho plus rho minus 0. K plus minus is called k star plus minus. K0 bar is called k star 0 bar, and then eta and eta prime for some strange reason are called omega and phi. Okay, just a remark. I think Prabhat will be interested in knowing this. So These are the vector mesons. Okay, fine. Okay, so this is spectroscopy, and what we have achieved in these classes is that we are now convinced that there is a color quantum number, and these quark wave functions or these hadron wave functions are antisymmetric in this color quantum number. So now that we have convinced ourselves that our elementary particles are electrons, heavier electrons, neutrinos which are paired with them, and then quarks which are like UD. Okay. So now this is the particle content of our universe. This is what we believe, and now we will go on to doing interaction. So now we are moving to the next part. So we want to look at interactions. So now we will only consider, until towards the very end, we will only consider interactions of elementary particles. So you can have electron scattering of a proton, but because the proton is not elementary, we will move that to the later part of these lectures, and we will only look at simple. For example, we will look at, say, electron muon scattering. Okay. And we will try and understand what we mean when two particles collide with each other in a way that is consistent with relativistic quantum mechanics. So what I will do is that I will set up the interaction picture that we understand from, you would have all done in college, maybe, I hope, in non-relativistic quantum mechanics, and then I will just use that analogy and set up the interaction cross section for relativistic quantum mechanics, and the whole idea of those interaction cross sections will be put on a very firm footing in the quantum field theory course. Okay, so I will not do that here. I will motivate it through what is called the Fermi golden rule. I think, has everybody heard of the Fermi golden rule? Is there somebody who hasn't worked out? Is there someone who hasn't worked out Fermi golden rule in non-relativistic quantum mechanics? Okay, everybody has done it? Okay.
Ma'am, I have not worked out.
Who is ma'am? Okay. You have not done? Aren't you a student of this institute? You didn't do golden rule? Fermi golden rule?
No, ma'am.
Okay. Did you do any scattering at all in non-relativistic quantum mechanics?
Non-relativistic, yes.
Yeah, I'm talking only about non-relativistic. Only non-relativistic. Then I will use that, and then I will make an analogy. I will then.
Scattering class, I think, it was left incomplete because of COVID situation.
Oh, okay. I see. So what is the situation with that semester? It's all complete, is it?
That semester, yeah.
Your previous semester is okay, fine. Oh, okay, fine. Okay, good Lord. Okay, fine. So then let me say a few words on that, and then I will. So let me start out from there. So what does scattering mean? Let us start out with scattering. Then we will come to the non-relativistic part later, but we will now. So the way we understand scattering is that somewhere at t minus infinity, I have a bunch of free particles. Okay, so that means I have a Hamiltonian H naught, which I can solve exactly, and it satisfies okay, and since this is a non-interacting state, I can write it in terms of I'm going to drop this H cross very quickly, okay? Fine, up till here, so it's a free particle evolving with e to the minus IET. Now what happens? Always the potential that you are considering under which the scattering takes place is always around t equal to 0 and lasts only for a finite time. And at this point, your interaction Hamiltonian turns on. And you will always assume that Hnt is small compared to H naught. So this is the perturbation theory approximation that we are talking about. And here We don't know what it is, there is some wave function psi. Okay, so psi is the wave function corresponding to h, and we don't know what psi is because now there are interactions. We can't solve this exactly. However, since phi n form a complete set, we can always write psi as okay. So we can write it as, by the way, an is a time dependent operator. Then what happens after the scattering? The detection of the scattered particles happens at t going to infinity, where h int is shut off and you have only the h naught and the bunch of. So you are going to find the scattering state as one of these phi n's. Is it clear? Sorry?
For how many times the H interaction keeps turned on?
It doesn't matter. It is a finite time. As long as it is not close to minus infinity or infinity, then I have these definitions where I can talk of at t minus infinity I have free states, at t plus infinity I have free states, and here I have interaction states which I can express in terms of this complete basis set. As long as I have that, I don't need to ask how long it lasts. These are all very difficult questions to answer. For example, I will tell you where if you take electrodynamics, you know that what is the range of electrodynamics interaction, let's say magnetism or electric force? Infinity. So then what do you mean by saying that it is turned on only for a short time? So all these will be made clear when we talk about writing certain endpoint Green's function and then getting the scattering cross section out of it. Okay. So I will not talk about it here. I don't want to go in that direction at all because this class is going to look at the phenomenology of these things. Okay. So suffice it to say that we can set up such a system. It makes sense. Yeah, ask.
I have studied that Fermi-Golden rule is valid only for constant potential and sinusoidal potential. Is it true?
No, not at all. Not at all.
Okay.
It is a way of computing things. Okay. It is a technology, and we are going to generalize that to a relativistic framework and apply it, in fact, to every interaction that we know of. Electromagnetic, weak, strong, everything. Okay. So except that now I'm starting out with this very non-relativistic thing, and maybe because some people have not seen Fermi-Golden rule, I will actually complete it, and then I will go back in the next class and show where we start to deviate from Fermi-Golden rule and where I will make the analogy with relativistic quantum mechanics. Okay. So maybe I will continue. Is it okay so far? So this is what I have. Okay. So what do I have here? Sorry.
I lost my connection.
Here, so I have free states at t minus infinity.
I know this. This is the second line. You were saying something about 5 to 10 minutes.
Sorry, what was I saying? Which particular part? Is it any equation on the board?
After you answered my question about the finite time.
So I'm saying that let us assume that this is true. So even though I'm telling you that electrodynamics, for example, has infinite range potential, okay, but still we are going to talk about somewhere we'll have free states. Even though we know that it's going to interact with the photon even at out to infinity, but somewhere at infinity we know that we are going to have free states, and then at far in the distant past we have a bunch of free states, in the distant future we have a bunch of free states. So these are what is going to be detected in the detector, and at some finite time, at some finite in some finite volume, the scattering potential is turned on, and therefore the new wave function psi can be written as a linear superposition of the complete set phi n. That's all I am saying. Okay. Is this picture clear? And what is the equation of motion for this? Sorry?
This is the time dependent perturbation we are talking about. As an have a time dependence.
Yeah. Because this is what is happening, right? It is evolving in time. That is exactly what we want to ask. After the scattering at some future time, What particular state is the system in? That is what we are asking. So that is why this is the setup, which is exactly what I am going to write. So I d psi by dt, if you want for once I will write h cross, is equal to h psi, right, which is h naught plus h int psi. So what is the left hand side? I am going to drop h cross, okay. So what is d psi by dt? I have two terms here dependent on t. So obviously I am going to get two terms. So I am going to get sum over n. So a n dot un e to the minus I e n t minus I e n a n un e to the minus I. Okay. Let me put a summation sign over here. So I just bring the I inside. So what does the second term look like to you? This I into minus I gave me 1. What does the second term look like to you?
This sign. Sign.
Is this clear? Is this clear?
Yes.
So I have I a n dot un is equal to h int of psi, and psi is don't worry that you can't see the rest of it, you know it's simply minus I e n t, okay. Now what I want to do is I want to find the a n's, right. That is the whole point of this exercise. I am saying that let us say that at t minus infinity or before the scattering occurred, let us say that the system was in a state alpha. What does it mean? What does it mean? A alpha is equal to 1, aj is equal to 0 for j not equal to alpha, right? Now I turn on the interaction and ask what happens. To ask what happens, I should find out what the AN are, right? So to find ANs, I use the orthogonality condition on UNs. So what will I do? I will multiply on the left by some UM star and then integrate over all x on both sides of the equation. So what will I get? What is the left hand side? This is a number, this is a number. So what is UM star UN?
Ma'am, is it delta function?
Yeah, correct. So that is delta function Mn. So the left hand side of the summation over n, it pulls out the single term which contains am dot. I hope you can hear the difference between m and n on this thing, and so this will also become e to the minus I E m t. Okay? And the right hand side is exactly the same. I mean, you can't do much with it. So there's summation over n u m star h int u n a n. Now what I'm going to do is I'm going to bring the e to the minus I E m t on the right hand side as e to the plus I E m t. And I'll bring the I over here and d cubed x. So here I have my solutions. My solutions am dots are this integral on the right hand side, and therefore what is the solution for am? Am will simply be integral of this over dt, right, because I have am dot over here. Now what is the dt over which I am integrating? Let's say that this around t equal to 0 is where we start, because that am dot is relevant only when I switch on the interaction. So let us say that I switch on the h int at t equal to 0, and then I am asking what happens after some time interval capital T. Okay, so this is what I have. So integral dt of this quantity, and now I can write this as minus I. Now what was sum over n? N was the initial state that the system started in, right? Now I am saying that the state started out with n equal to alpha alone. So the whole summation on the right hand side, n is replaced by, sorry, what is this an? N is replaced by alpha alone. So I have only alpha over there. The summation term drops. So I have integral d cubed x u m star h int u alpha a alpha e to the I E m minus E alpha t dt. And this is the only term which contains t. So you can see that this, therefore the x dependent part, I can write it as I just kept that a alpha just to show you that it's there, but a alpha is equal to 1 and every other aj was 0. Sorry?
Yeah, can you explain again how the summation established is? And t is equal to minus infinity, there is only alpha, but later on, like.
Before the interaction turned on, the system is in one of the eigenstates alpha. Okay? Since it's in one of the eigenstates and this is a normalized wave function, a alpha has to be 1 and all the others are 0, right? Because phi was a normalized wave function, so a had better be 1 and the others have to be 0. Is it clear?
Yes, yes,
Oh.
that is clear.
Okay.
I'm asking, that was at earlier times. Now,
No. So now we are asking now because we're going to integrate from the time when the potential was turned on. At that moment when the potential was turned on, the system was in a alpha. Sorry, was in phi alpha. Okay, and then we are asking what is it that it can transit to? It can transit to any one of these m's, and the probability of transiting is what we're going to find out. And this m is we're going to ask is this, right? We will then solve. Once I know what m is, what all m's are non-zero at a time capital T, then I can write psi in terms of those am's at some future time capital T, right? Is it? Yeah. So this is what I have, and you can see that this is the only integration that I have. So this integration will be e to the I em minus E alpha t by I Em minus E alpha from 0 to t, right? So from 0 to t, this will be t minus 1 by this denominator, right? When t is equal to capital T, when t is equal to capital T, I get this, and when t is equal to 0, I get this, and minus I and I will cancel to give you a sign. So let me just write it as 1 minus. Is it okay? Yeah. There are some questions, but I'm not able to hear them.
Hello.
Yeah, ask. Huh? Can you speak a little louder? I'm not able to hear anything that you're saying. Koina, is it?
Yeah.
Ha, sorry. Ha, yeah, now better. Yeah, tell me.
Yeah. So we are writing
Sorry, can you start again? I'm not able to hear you.
I'm saying that we are writing the child.
I'm really sorry. Is anybody else able to hear her and can relay the question?
No one Koina's voice is very low.
Okay.
No, audio gets low.
Yeah, I think when you start out, it's okay, but then I can't hear the rest of it.
Maybe she can write it in chat.
Write it in chat and somebody read it out because I'm nowhere near the chat window. Okay.
Sure.
Yeah. Thanks. Yeah. Thanks. Yeah.
So Koina is saying she's writing now.
Yeah. We'll wait. We'll wait.
Yeah.
Ma'am, so golden rule is this formula.
No, we still have to do a little more. We're halfway there.
Ma'am, till here we have done in our course, but
This is like this Abhimanyu's Chakravyuha, right? You have to get out again. You have to complete this by writing the probability, right? Now you have only a probability amplitude. And you have to complete it because there is a t here which is arbitrary. So we'll complete it. We'll complete it in a moment. In fact, while Koina is typing, I was not planning to do this. Let me look at my notes and make sure I'm getting everything right.
Could we have done this if H have depended on time H interaction? I mean, could we have taken it out?
Sorry, one second. I'm not listening to you because I'm looking at my notes. Just give me one moment.
Okay, ma'am, this is the question from Koina.
Okay, sorry, yeah, okay, okay. First, Koina's question, yeah. What is the question?
Okay, size introduced due to the interaction, and we write it down as a linear combination. However, why do we suddenly consider only A alpha to exist?
Why do we suddenly consider only?
Only alpha to exist.
Oh. Here, we are starting at 0. See, we are integrating from 0 to t, right? What is 0? 0 is the point at which the interaction Hamiltonian is turned on. So from t equal to minus infinity, once it is in some eigenstate, it remains in that eigenstate, right? So therefore, that is the time evolution. It's a free particle. This H0 is a free Hamiltonian. This is simply sitting in some state. Let's call it phi alpha. So this is what I called it, phi alpha. So it stays as phi alpha, phi alpha, phi alpha, phi alpha until t equal to 0. Then when the interaction Hamiltonian is turned on, this phi alpha transits to some phi m, and it can be many phi m's, and each of them with a probability which we will find out, which is given by this coefficient term, right? It is just a choice. I mean, the system you could have taken to be, let us say that it was in some other state phi beta, but that doesn't matter. It is in some initial state. Because there was no interaction, the system is in one of the eigenstates, and we call that alpha. Nothing more than that. And it remains like that until some interaction, right? When there is no interaction, the state simply sits over there in that eigenstate, and we don't know what it is. Then when you turn on the interaction, it flips to some other state, phi m. Maybe I could have called m as beta, but since I started out with n, I put m over there, but you could have called it beta, and then maybe that would have seemed nicer to you. There's not just one state m. There are many possible states m. And for each of them, the probability amplitude is AM. Is it clear? Koina, does that satisfy you?
Yes, got the point. We got the point.
Okay, very good. Okay, so okay, very good. So now we are here. So this is the probability amplitude that a system which started in state alpha is going to be observed as state M after a time capital T. So what will be the probability? The probability that some state which started out in alpha goes to state M is given by AM squared, right? That's really the probability. The coefficients give you the probability that you will find the wave function in state phi M, right? So this is AM squared. So that will be UM H int U alpha squared, and then I have to square this, right? So let me just write the denominator squared. So you can see that this is a complex quantity. I have to mod square it, and you can, there's no higher mathematics involved. It comes out to be sine squared Em minus E alpha T by 2. You have to multiply 1 minus e to the I times 1 minus e to the minus I. You will get a 1 minus cos, which I have written as sine squared, right? Because I have used cos theta is equal to 1 minus 2. So there will be a 4 sine squared theta by 2. Okay? So this is what I have. So now we are reaching what Fermi called his golden rule, and I will show it over here. Before we do that, I'll make some remarks. So you can see that the probability is large when the new state M is very close in energy to this original state alpha, because there is this energy denominator. Okay?
Yes, sir.
That is the crux of Fermi golden rule, but just for completeness, let us complete this. This is of course some matrix element, and this tells you that this is some kind of sine squared function. So it tells you that it peaks again when Em is equal to E alpha, and then it goes down from there. Now the question is this: I may not have one state M, I may have many states M. So I can think of a continuum limit. Let us say that alpha is here, and there's an entire bunch of states M, and they are all very close. Because they are all very close, what Fermi said is you can make the approximation that this quantity is independent of M, because all the transitions to this state, this state, this state, all these states will be approximately the same. The matrix elements are not very different. So I can take this out as some constant quantity independent of M. Then I can ask, what is the total probability of transition to any of these states? So that will be P. Sorry?
Is it M degenerate? That is what you are saying.
No, there are many. It's a continuum. I am not having discrete states. It's a continuum of states. Why am I saying that? These are scattering states. So maybe I should pause here and find a piece of the blackboard. Maybe here.
One person is not able to.
No. Let us just answer this question first. So what we are saying here is that we are looking at scattering states. This is not a bound state problem. Very important for you to understand. Okay. So in bound state problem, I am used to having. Oh, what happened? I thought I had written my. Which one is outside here?
Vaibhav is outside class. Vaibhav is not able to join. He left, maybe there is some issue.
But I mean, Prabhat was.
We get some connection issue.
I see.
Maybe some connection issue there.
Okay, I mean, is he trying to enter and we didn't give him? No, he's in the waiting room. 1 second, I'll admit him. Yeah, he has come back. Okay. Is it okay, Vaibhav? Are you able to listen and hear us? Okay, fine. Okay, so where was I? Sorry. So here when I have bound state problem, you're used to solving, all of you have written in your entrance exam, right? All of you gave interviews of harmonic oscillator, square well, all discrete states, right? But now we're talking of scattering states. These are free particles scattering off each other. There's no bound state problem. So what you would be more likely to see is a continuum of states. Why? Because one may have momentum 10 MeV, then 10.1, 10.2, 10.3. There are so many states available to those final state particles that you can think of them as a continuum of states. And you can take the continuum of states which is very close to alpha, because you know that this energy denominator will otherwise kill your probability for transition. But this probability then, the total probability, is therefore the sum over all m of am squared. Okay, and this sum over m in the continuum limit I can write as an integral over all these states. So I can write it as integral dn, and I can assign the energy En, and I can replace this entire equation with Em going to En. Is it clear? So what I have done is that this is the probability of transition to one particular state m, but if I can think of a continuum of states m, then I have integration over dn of these states, okay. And now I can do the final thing. I can replace dn as dn by de into de. So I can convert the energy, the integration of from n to e, and because this energy denominator will kill states which are very far away from E alpha, I can simply extend the energy integration from 0 to infinity. Is this clear? What all steps I have done? This is the probability for transiting to one state m. There are many continuum of close by states. So total probability will be a sum over all those states. In the continuum limit, I make the sum into an integral, and m is the number of states n, and I replace the dn integration by de integration, and because this energy denominator takes care of everything, I can integrate now from 0 to infinity, and this sine squared will just give you a factor of pi. I don't know whether you remember these formulae, but 0 to infinity sine squared of this quantity will give me pi. Okay, so
ma'am, this total probability am square, sum over am square, ma'am,
yeah,
this is like not including the initial state.
no, it's always from, this is the probability from alpha, right? Alpha to some state, some collection of states n, right? Always alpha was the initial state, that never changes.
Sum over all n, we get 1, right?
It is summation over all n.
If it's sum over all n, probability, we get 1. Probability the particle will go anywhere is 1, right?
No, 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 no. How can it be? Because if I take the state which is so far away, the energy denominator will kill it, right?
But we are summing over m also.
Yeah, but those are all the states that it can, that are available to it, right?
And there's only one continuum.
Yeah, yeah. There are so many states available. I mean.
Okay, m is a subset of.
Yeah. So I am not. This integration is either pi or pi by 2. It's pi. So let me just write down the answer. The integration is, yeah. So okay, the steps I will tell you. So I have Em goes to En. So I have a term which looks like En minus E alpha into T by 2. So I will call it some x. So then I will convert Den to dx. So then I will integrate 0 to infinity and now sorry, so the states I number, so this is alpha, so I will go infinity below alpha and infinity above alpha. So in fact I will take the energy from minus infinity to infinity. So this will be the answer. So when I put them all together I get P is equal to sum over m P m alpha of t is equal to 4, then the matrix element squared is still there, that doesn't change, sorry, so 2 pi, I am putting back the h cross, and this more or less is Fermi golden rule. Okay, so we are not interested in this. I want to break away at the point where we solved for AM. Okay, where we solved for AM is where I want to break away and do the relativistic generalization. But this is just for completeness since you had not seen it. So this is Fermi golden rule. So this is the matrix element which is constant. We have taken it out of the brackets. So for this was actually m h int alpha, but I've taken it to be the same and I've taken it out of the integration. That's why I could do the integration. And what it is saying is that the probability of transition increases with time, obviously, and is proportional to this quantity, which is called the density of states per unit energy, or the number of states, where density of states is number per unit energy, Okay, so this is the important result that Fermi showed, that what you really ask now, the physical quantity, because this is not a meaningful quantity, is you ask for the, I'll just finish this sentence and then I'll answer, someone is asking, transition rate is equal to dp by dt, it's called W, and it is simply 2 pi dp by dt, 2 pi by h cross squared. So that you don't know what that capital T is and you get rid of it because you're asking what is the transition rate, which is the transition probability per unit time. So that T just goes away and that's what you have. Okay, some question?
Yes, ma'am.
Yeah.
The density of state is independent of energy. So you
No,
take it
it's
out
not
of
independent of energy. The density of states is not independent of energy. This transition from the Hamiltonian has some term in it, which is the interaction Hamiltonian, which takes you from alpha to any one of these m's. The assumption that we have made is that each one of these transition probabilities or matrix elements is the same, and that I have taken out as a common quantity. Okay.
Ma'am, but will this simplify the question too much, ma'am? Because
No, it doesn't.
interaction will be
It doesn't, because what you will see is that, maybe I will draw it diagrammatically. I will draw it here then. So if I draw the probability as a function of, I draw the probability as a function of Em minus E alpha. So you can imagine that when Em minus E alpha is 0, the probability is maximum, and then it dies out here and goes to 0 at these points. These points are determined by, oops, okay, these points are determined by sine squared Em minus E alpha t by 2 going to 0. Okay, that means Em minus E alpha t by 2 should be equal to pi, right? So then Em minus E alpha should be equal to 2 pi by t, right? So this is 2 pi by t. When this is 2 pi by t, 2 and 2 will cancel, t and t will cancel, and this is pi. Sine squared pi is 0, sorry, this is 0, okay. And this will be, of course, minus 2. That's why it's symmetric, because of the sine squared function. Okay, and you can see that this is very small compared to this. So you're saying that only the small interval over here, these states which have Em minus alpha as 2 pi by t, okay. So which are very close because t is very large, right? You are looking at it at very late times. Since t is very large, only in a very small central region is there any appreciable transition probability. In that region, I am entitled to take this quantity to be the same for all the states m. Is it clear? Because anyway the contribution from minus infinity, so my contribution is from minus infinity to plus infinity, and those you can't see that side of the board, but it's okay. And anyway there is no contribution at all from those terms because this integral converges very fast and only a small fraction of it contributes over here. Is it clear? And by the way, there is I think there is this is yeah, okay, there is some h cross here. I can't remember. Somebody put back the h cross. Okay, so delta E delta t is h cross, right? So this should be h cross. Yeah. So in this course, I will be very shoddy. We will drop the h crosses very soon. Okay, but just in the beginning 2 lectures, I am just trying to keep it. Yeah, I think yeah. So then t by h cross is probability. Yeah, this is 2 pi h cross by t. Okay, so this is the kind of very narrow resonance region, and that's why you are allowed to do all this, or rather, this is why Fermi allowed himself to do this. So this is the standard way in which the calculation is done. All I want to point out to you is that the transition probability depends on the density of states here, and that you can see because in the same region from minus, let us say this is the region from minus 2 pi by t to 2 pi by t. So if I have 3 states here, or if I have 155, obviously the contribution is going to be different, right? Geometrically you can see that, and therefore the transition rate has to depend on the number of states available to you in that energy range, okay. And that energy range is not over the entire energy range, but really what is going to dominate is this small energy range. Even though for purposes of getting an analytical result, I have integrated from minus infinity to infinity, right? But really the contribution of that integrand is only coming from this central region, and so we are not really wrong, okay. So this is, anyway, let me say this is all non-relativistic quantum mechanics, and what we want to do is we want to write such a transition probability amplitude and hence the transition probability in the relativistic case. Now since there is not much time, I will just make a few remarks, so it's your choice. We can either stop a little early today, or I can make some remarks on relativistic quantum mechanics. You want to stop or you want to continue? The first person who answers, I will do whatever they say. Okay. Who was that? Frame. Okay, fine. Okay. So this is the basic setup that I am going to use to tell you what are transition probabilities, and from there how we find scattering cross sections. But let us review a little bit of relativistic quantum mechanics, so that since all of us are from different places, and as I said, I keep saying I really miss being able to see your faces because I am not sure whether it's too fast, you're understanding, not understanding. So I will appreciate if you stop and ask. Of course, at some point, if I can't explain further, that is my limitation. I mean, that can't be helped. But let us look at quantum mechanics, okay? So let us start. What is the non-relativistic Schrodinger equation, for example? So I write E is equal to P squared by 2m. Then I write an operator equation, which is H psi on this operator acts on some wave function, and the P operator is minus del squared by 2m. Psi, okay. There is some H cross squared, right? Some H cross squared is there. In the presence of a potential, E goes to E minus V. So I get E minus V psi is equal to minus H cross squared del squared. And this is called Schrodinger equation. Now let us look at the relativistic case. I have E squared is equal to P squared plus M squared. Now I make this an operator relation and act it on some state. So I can write E as E or as H, it does not matter, is equal to minus, let us write the operator as E psi is H, psi is equal to I d by dt psi. Okay, so I have minus, okay, there is an H cross squared, I am going to drop that, minus d squared psi by dt squared is equal to, so this is P I d by dx. There is an H cross over here also, minus del squared, let us write it as d squared by dx squared. So this is called a Klein-Gordon equation. I don't know whether you have seen it.
Yes, ma'am.
Yeah. So this is the relativistic corresponding relativistic equation for a spinless particle when you upgrade Schrodinger equation to be consistent with special theory of relativity. Okay. Now here we had the notion of probability, and we had the probability density was called psi star psi. And this was conserved in the sense that the particle has to be somewhere in space, and therefore its integration over all space has to give you 1. This is the reason you want to have normalizable wave functions, right? This is the notion of probability in non-relativistic theory. However, that is not a good quantity over here. So let me first write down what we call the probability density in relativistic quantum mechanics and then explain why it should be so. Okay, so let me write this equation down. So I have del d squared by dt squared minus del squared, let's call it plus m squared psi is equal to 0. Now I can left multiply this by psi star. I get one equation. I can also take the complex conjugate of this equation, which is and I can right multiply it by psi. And ask what happens when I subtract these two equations. So I get psi star d squared psi by dt squared minus d squared psi star, sorry, dt squared psi minus psi star del squared psi minus del squared psi star. So these two terms cancel. Okay, and you can see that these two terms are just this, because if I act dt on the second term, I get psi star d squared psi by dt squared. If I act it on the first term, I get d psi star by dt into d psi by dt, and that cancels when I get d psi star by dt times d psi by dt from this second term. Can you see that this is exactly this term?
Yes, ma'am.
Similarly, can you see that this is and I'll multiply both by I. And what I will get is an equation which you will recognize as what is this equation?
Continuity equation.
Very nice. Everyone has seen this? If I integrate this over all space and I use the surface term goes to 0, then it tells me that integral d rho is conserved, right? So rho is a constant in time, that is the conserved quantity, but you can see that if I write this current in terms of a 4 vector current which contains rho and j, then rho is I psi star d psi by dt minus d psi star by dt psi, comma, minus I psi star del psi minus. Okay, so it is this quantity, and therefore for relativistic consistency this is the quantity that I must identify as the probability density and not just psi star psi. Is this clear? Is this clear? So
Yes, sir.
this equation therefore, for example, let me take a free particle solution, psi is n e to the minus I e t, some h cross is there. Then what is rho? Rho is so rho will be n squared because psi star will give me an n star and psi will give me an n, and so this will be e to the plus I e t times d psi by dt will give you a minus I e, and e to the minus I e t which will cancel with this, and the second term will give you again minus I e, and there is an I in the front, so there is a that's equal to did I do this right? D psi by dt gives me minus I e, and this will also give me a minus I e because this will be plus I e, it will be minus I e. Oh, I into minus I is plus, sorry. So this is gives me 2e. That's good. Okay. Is it okay? So that means if I integrate over rho over all space, this wave function is normalized wave function, some whatever it is normalized to in some volume V. It tells me that there are 2e states for, let us call it unit volume, it does not matter. So in the Schrodinger case, we had integral of rho is 1. Here we are saying integral of rho is just going to be 2e times some volume element which we can set to 1. That is a normalization constant. Okay. Why is there a difference between them? You can see that this is a 4 vector, this is the time component of the 4 vector, this is the space component of the 4 vector, and therefore rho must not be a constant, cannot be a constant probability density, it must transform like the time component of a 4 vector. And we know that there is a vector which is the momentum 4 vector which has energy as its time component. So there will be some, okay, see C H cross all are 1, okay. So please put them back in, I mean I am not sure, they are there somewhere, but we are not worried about it. So you can see that therefore rho transforms as E, which is a time component of another 4 vector, right. And therefore we can see that rho has the right transformation properties relativistically and therefore it cannot just be psi star psi, but it has to have this form. Is it clear? So we have learned two things here. We have to generalize our notion of what rho means, the density means, and also that we now have therefore to normalize this to 2E states per volume V or per unit volume. So this is the first difference that we have between the relativistic and non-relativistic cases. Okay, so I will stop here with this remark, and in the next class we will set up more things. We will take a simple case of Klein-Gordon equation and set up this probability amplitude AM for the Klein-Gordon case. Okay, I will stop here. Is it okay?
Ma'am, if we make a Lorentz transformation, then this probability, total probability will change.
Yes, because it is not a Lorentz invariant. It is the time component of a 4 vector.
Yes, that's why probability will change, total probability.
No.
Of the particle that's...
No. Okay. I will write it here. Integral rho d cubed x. Rho transforms as a time component. So let us apply a Lorentz transformation. It's like a time component of something, right? So how does a time component, okay, how does it, let us take the usual x mu.
1 by root 1 gamma, will multiply gamma.
The other way around. This goes as 1 by gamma. Space contracts, right? So space contracts, so d cubed x prime rho prime is d cubed x by gamma, and time dilates, so this will be gamma rho, that is rho d cubed x.
Okay, so gamma can...
Yeah, so that's very important, because that is why, so rho d cubed x is an invariant, and that is an invariant only because rho transforms as a time component. Okay, so the total density is conserved, so it still makes sense to talk about probability density of states and that it is conserved, but that is only possible when rho has this definition and not psi star psi. Okay?
Yes, ma'am.
Yeah. Okay. Anyway, we will go on. This is just the starting point. We will continue.
Ask. We learned that there are some difficulties of interpreting Klein-Gordon as probability.
No, this is a fine probability.
Like we learned that it's there are some difficulties of interpreting Klein-Gordon equation as probability density in some books.
I mean, in what sense are you asking this question? I mean, Klein-Gordon is a perfectly fine.
There are some issues with Klein-Gordon, right? Equation.
I mean, this sounds very generic. If you tell me specifically what the problems are, I can tell you. Because, I mean, if you're talking about field theory, I'm not talking about field theory. I'm just talking about writing it as a relativistic quantum mechanical equation and identifying a certain probability, definition of probability density rho. That's all.
Okay.
There is no difficulty at this point. I mean, the quantization, what they call writing the quantum field theory, all that is a different problem. But right now at this level, as a relativistic quantum mechanical equation, there is no problem over here. I have a 4 vector current here. I have a 4 vector current which is conserved. So my density is integral d cubed x, therefore is a conserved quantity in time, and so I have nice behavior. And I have a nice physical interpretation of this quantity, provided that it transforms like the time component of a vector. Okay?
Yes, sir.
Okay. Okay, then I'll stop here. I'll continue in the next class.